Substitution reactions of halogen alkanes with water. The reactions between halogen alkanes and water. If the halogen alkane is heated under reflux with water, the halogen is replaced by OH to give an alcohol. There is only a slow reaction between a primary halogen alkane and water, even if they are heated. But it is faster with the secondary and tertiary alkyl halides. The reason is because a primary alkyl halide is less reactive compared to the other alkyl halides, and water is a weak nucleophile. When both react, their reaction will be very slow. Let us use examples and see how primary, secondary, and tertiary alkyl halides undergo substitution reaction using water nucleophile. Bromoethane is reacting with water to give ethanol. Iodopropane is reacting with water to give propanol, and methylchloropropane is reacting with water to give methylpropanol. Mechanism for substitution of bromoethane, a primary alkyl halide, with water. Here we have two chemical species, a nucleophile, which is water, and bromoethane, which is a substrate. Bromoethane has acquired partial positive and partial negative charge due to high inductive effect of bromine in the molecule. Bromine is partial negatively charged because it is withdrawing electron from carbon, which becomes partial positively charged. The positive charge of carbon is attracting the electrons from the water molecule, and these repel the electrons of the bond between bromine and the carbon by breaking it and form bromide ion and an oxonium ion. An oxonium ion, it is an ion in which oxygen has formed 3 single covalent bonds. And because there is a positive charge on oxygen, this molecule is highly unstable. And to stabilize the molecule, a base is needed to subtract a proton from the oxonium ion and form a stable molecule, which is an alcohol. That's why the water molecule, which is acting as a base, is going to donate electrons to one of these hydrogen, and these electrons repel electrons of the bond towards oxygen, and this forms another lone pair and removes the positive charge on the oxonium ion. This will produce an alcohol and a hydroxonium ion. This reaction happens in 2 steps. The first step is slower than the second step because the first step, which consists of breaking the bond of bromine and carbon, is higher endothermic compared to the second step. So, the activation energy in the first step is higher than the activation energy in the second step. The slow step always is the one which determines the rate of reaction. So, the rate determining step is this step of formation of oxonium ion. Because the slow step is involving 2 chemical species simultaneously to form the product, the mechanism is called SN2 reaction, which means bimolecular nucleophilic substitution or nucleophilic substitution of the second order. Reaction of tertiary halogen alkanes and water mechanism. Here we have a tertiary alkyl halide, which is an alkyl halide having chlorine attached to carbon, which is the tertiary carbon. Because of the positive inductive effect of the alkyl groups around this carbon, if it is dissolved in a polar solvent, it can undergo self-ionization and produces a stable carbocation. The stable carbocation formed is having a carbon which is octetly unstable. To stabilize the carbon, a nucleophile in the medium, here it is water, is going to donate electrons to this carbon by forming a new covalent bond, and it gives an oxonium ion. This oxonium ion formed is not stable because there is a positive charge on a high electronegative element, which is oxygen. So this is stabilized by a base in the medium, and here water is going to play the role by donating electrons to this hydrogen attached to the highly electronegative oxygen. And if the electrons are donated to this hydrogen, they will repel the other electrons of the bond between hydrogen and oxygen, and this forms a lone pair on oxygen, and it removes the positive charge on the oxygen, and the molecule becomes somehow stable. The formed alcohol is a tertiary alcohol and a hydroxonium ion. The reaction happens in 3 steps, but as we said it in the previous example, one of the 3 steps, it must be a rate determining step. And which one? The rate determining step, it is always the step which is slower than others. Here, the first step, it is slower than others because it is highly endothermic than the rest of the steps. So, we are going to count how many chemical species are involved in this rate determining steps. You can see it is only the substrate because the nucleophile comes in the second step. As it is only one chemical species involved in this rate determining step, this mechanism is called SN1. SN1 means unimolecular nucleophilic substitution or nucleophilic substitution of the first order. Reaction of secondary halogenalkenes and water mechanism. We have seen the reaction of primary alkyl halide with water, which followed the mechanism SN2 or bimolecular nucleophilic substitution. We have seen the reaction of tertiary alkyl halide with water, which followed the mechanism SN1 or unimolecular nucleophilic substitution. What about now the secondary alkyl halide? How does it react with water? Is it SN1 or SN2? The answer is, it is going to react using both types of mechanism, either SN1 or SN2, depending on the conditions. So, don't hesitate to pause the video and try one of these mechanisms because they are much similar to the ones we have seen in the previous examples. Let us start with SN2 mechanism. The alkyl halide, which is polar because of inductive effect of iodine, is going to cause carbon to carry a positive charge, and this positive charge is going to attract electrons from the nucleophile, which is water here, and form new covalent bond. But these electrons which are coming from water will repel electrons of the bond between the carbon and iodine, which will result in the formation of an oxonium ion and an iodide ion. The oxonium ion formed is not stable because there is a positive charge on oxygen, which will cause the hydrogen attached on it to become very labile, and any base in this medium will attack on one of these hydrogen and deprotonate the oxonium ion. When the bonds of hydrogen and oxygen is being formed, another bond of hydrogen and oxygen which was existing will break, and then all electrons will migrate towards the oxygen atom, and the charge is removed, where it will end up by forming an alcohol and the hydroxonium ion. As you can see here, it is happening in 2 steps like the primary alkyl halide. But the 2 steps are not all going to determine the rate of this reaction. The only one which determines the rate of the reaction is the slow step. And the slow step is the first step where there is breaking the bond of carbon and iodine. And the second step is fast and is not considered when we are looking at the rate of reaction. And the first step, which is slow and is rate determining step, is going now to involve 2 chemical species during its processing. What are those chemical species? Water molecule, which is a nucleophile, and the alkyl halide, which is a substrate. So the rate of reaction will depend on both. That's why we have this reaction, which is bimolecular, 2 molecules, nucleophilic substitution. So you can also try the unimolecular nucleophilic substitution of a secondary alkyl halide. Here what happens, the alkyl halide will undergo a self-ionization and produce a somehow stable carbocation because the carbon, which is positively charged, is stabilized by the 2 alkyl groups around it, and it makes somehow the positive charge neutral. And then the positive charge is going to attract electrons from oxygen of water to make a covalent bond and make this carbon octetally stable. When this happens, an oxonium ion will be formed. As I told you, an oxonium ion is not stable because there is a positive charge on oxygen, which is very electronegative. That's the reason why the base in the medium and water is the one is going to deprotonate the oxonium ion so that it can remove the charge on oxygen and form the alcohol, which is more stable than the oxonium ion. After forming the alcohol, now we have a hydroxonium ion, which will be the acid in the medium. So we have here 3 steps, but as I told you, one of them must be a rate determining step. And which one is that? It is the one which acquires much energy when it is happening. And then which one requires much energy when it is happening? It is the first step, because it consists of breaking the bond, which is a highly endothermic reaction. The rest of reactions, they are less endothermic reactions, and some of them are even exothermic. So because the rate determining step is involving only one species, in order to form the product, it is unimolecular nucleophilic substitution.